Okay. So we have Carla today. Welcome, Carla, to our winter school, and we appreciate your presence here. Carla is a professor at University of Pompeu in Fabra. She's an assistant professor, and she's known for her work on zero knowledge proofs in practice. Before joining Pompeu University, I think she received her PhD from University of Catalonia, Polytechnic University of Catalonia in Barcelona. Please correct me if I'm mistaken. And after that, she was a postdoctoral researcher in Ruhr University in Germany. And today she will be talking about this variant of universal and updatable SNARKs, which are very interesting for practical applications. Welcome, Carla. Please start.
So, okay, so I will talk about techniques in universal and updatable SNARKs. So I guess after this nice introduction, you know a little bit what that's about. You also had a very long introduction by Jens yesterday. So first I will do some reminder of the basics, but I think that should be covered, but what you've already seen. And then I will talk about the technical core of non-updatable and universal SNARKs, because I want to highlight so the technical core of these first non-updatable and universal SNARKs is already very good to illustrate the main ideas on how to build a SNARK. And second, because I also want to highlight what are the difficulties in coming up with this more general type of SNARK, we just use universal and updatable. Then I will talk about setups, like how they were carried out in practice. By this I mean the ceremonies that were carried out to generate the structured reference string.
Excuse me, Carla, I'm interrupting you, sorry. So I guess you are explaining second slide, but we are, unfortunately, it's frozen. We just see the first slide. Maybe you can retry.
Okay, so, and finally, I will talk about the technical core of universal and updatable SNARKs. I wanted to talk about future directions, and I'm not sure how far I will get, and finally, I will just maybe just highlight what are the useful research directions. So you've seen that already. So what are zero knowledge proofs? Well, you know, it's a process in which a prover probabilistically convinces a verifier of the correctness of a mathematical proposition and nothing else, right? The classical example is Peggy has there is an unsolved Sudoku, that is a statement, and there is a solved Sudoku, which is and the witness, which is some kind of certificate that a solution exists, is the solution of the statement. A zero knowledge proof aims anything else. As you know, there are many things we would like to prove in zero knowledge. For instance, we could show that we know the secret key of an RSA crypto system, or that I know the secret key associated to some crypto system more generally. But, sorry, let me connect. But in this talk, we will mainly talk about very general statements like this one. So this is the circuit satisfiability problem that tells me that given some kind of circuit, I know a witness for satisfiability. So that means I know an input of the circuit that evaluates to 1. This is done for several reasons. One of them is that circuits naturally encode computation. And the other reason is that, as you probably know, circuit satisfiability is an NP-complete problem. So if I can create a proof for such statement, I can create a proof for any statement at some cost, of course, because I have to reduce the statement in this form. You've also seen that, for sure you saw that in Jens' talk, So we have that the main properties, I just refresh them because I will refer to them, are completeness, soundness, zero knowledge, and then there is this property that I will not really mention, that it's of knowledge. Completeness is just classical correctness, so it just tells me that if everybody behaves in the specified way, the protocol, the victor will accept. Soundness tells me that Peggy cannot cheat. And zero knowledge tells me that Victor learns nothing beyond the truth of the statement. So Victor learns nothing from this interaction apart from the fact that the statement is true. But he doesn't learn anything about the witness. So zero knowledge proofs are it's a very complex primitive. I'm sure you realize this by this point. And the point is that there are many parameters and many trade-offs that are possible. So the first one is expressivity. So as I said, you can prove different things. So, and of course you would like to prove something as general as possible, right? Like circuit satisfiability would be a very good example of a very general statement. But of course, this comes at a cost. So the more general statement, this means also that you have less efficiency. So it means that you have higher prover complexity or verifier complexity, potentially bigger proof size, so larger communication complexity. You also have weaker or stronger computational assumptions. There's also, and this will be very important in this talk, there are also trade-offs in having a setup or not having a setup. Usually if you give up having a trusted setup, then you need to have a longer verifier. And also, even if you need some kind of trusted setup, well, there's a different quality in that, right? Like you can have, as we will see today, you can have a setup that is updatable or not. Finally, there's amount of interaction, right? You can have interactive proof or non-interactive proofs. Then there is this notion of knowledge that refers to the fact that the proof might guarantee not only that a witness exists, but that Peggy knows that witness, or you have sometimes private versus public verification. It is often much more interesting to have public verification because this means that actually Victor can be anybody. So really anybody can verify that the statement is true, whereas in private verification, it's only a designated party that can check that the statement is true. So in this talk, we will focus on pairing-based zero-knowledge SNARKs. So the title doesn't say anything of pairing-based zero-knowledge SNARKs, but this will be our focus. Why? Because in some sense, these are the most efficient. So definitely when we look at the verifier, right, at the concrete cost of a verifier. So the setting I will be focusing on this talk is a setting where we have the language we are talking about is circuit satisfiability. Size, number of operations. Obviously, it will be also a public verifier. The proof will be succinct. So this is like something very powerful. This is why SNARKs are called succinct interactive arguments of knowledge. Succinct is in one of the keywords because it's an essential property that tells me that no matter how big is my circuit, no matter how big is the statement I want to prove, the proof is, in this particular case, will be constant, okay? And finally, one of the drawbacks of this family of SNARKs is that they have a very long structured reference string. In fact, we will see that we need a reference string that is as long as the size of the message. Finally, another drawback is that this family is based on very strong assumptions, and hopefully we will see these things as I proceed. So just to give you a brief idea, so SNARKs are really very useful because it means that we have a super efficient verifier. We have a party that computes the proof and then can disappear, go offline. Anybody can verify the proof, doing very, very little work. And this is why we talk about the hunting of the SNARK, because SNARKs are a very attractive creature that is worth pursuing, but it was really hard to find efficient constructions of SNARKs. And the title of The Hunting of the SNARK is inspired by a poem of Lewis Carroll. In which the whole idea of interactive proof system and something is something that already originates in the 80s. And there are some things in between. So there were like these succinct arguments of Kilian and Micali, but they were not truly efficient in a practical sense. So, and then in 2010, this started to change, where when Groth proposed these succinct arguments without PCP, so with bypassing these techniques of Kilian and Micali. And then in 2013, we had this very good, very interesting, this breakthrough, this paper by Gennaro, Gentry, Parno, and Raikova, if I'm not mistaken, where they introduce, they really reduce these large proofs to a very, very short piece. And this motivated people to really started implementing this in practice and using SNARKs for proving financial transactions and so on. And this brings us to 2006, where Groth really had a pairing-based SNARKs that was super efficient. So it costs only 3 group elements to prove that a statement of arbitrary size was true. Okay, so this is, and this continues. This is really like a kind of literature and that has grown exponentially. There are many people this is based SNARKs that are really interesting for practice. So, and then before I talk about further development, so before I talk about this point so much more and universal and updatable SNARKs, I want to focus on these ideas here. So the ideas that brought to designing the first constant size pairing-based SNARKs. So I will not present a very concrete scheme. So it's a mixture of this result of 2013, but ideas are close to what grows also the most efficient SNARKs. Because at the end of the day, all these pairings, all these pairings-based SNARKs, there are different optimizations, but they are based on similar ideas. So let's move to talk about this. So I hope after this talk you have a better idea of how to construct a SNARK. And this is something I would like to take out of this talk, so that SNARKs are usually built in 2 steps. Well, there is usually an information theoretical step where all we are doing is rewriting the statements. Okay, so we have a very large statement that tells me that a certain circuit is satisfiable. We have a witness for satisfiability, and then we write this circuit relation as an algebraic relation. Okay, so there's nothing for now. This is just a rewriting, and then the essential point is that we remodel this algebraic relation as a polynomial relation. So this algebraic relation is written in the form the circuit is satisfied if the certain polynomial divides a certain product. Okay, why is this interesting? For now, note that here nothing happened. Okay, so all these are very large statements, the 3 of them. The point is that once we have written these statements as a polynomial problem, we can do a compressing step, which is a computational step. This is an information theoretical step because I'm doing nothing, I'm just rewriting the circuit. And then we come to a computational step where a statement is compressed using cryptography. And the idea is that once the statement is written in terms of a polynomial relation, we can verify this relation at a single point, okay? The point is that cryptography will ensure that although we are only checking for the point of view of the prover, he doesn't really know how to exploit this. From the point of view of the prover, it is as if the full polynomial relation was being proven. So for this,
Carla, sorry for interrupting you. I have a question. So
yes.
So can you give us an intuition that from the context of blockchain or coins or zero coin or whatever, how come, so which statements are translated into this kind of circuits? So what are the original statements that one needs to prove?
Okay, so one need to prove things like I have the secret, so I have the address, so I'm the owner of this amount of coins and I want to transfer it to somebody else, something like that, okay? So which means that I have, so the difficult part is that I have to write this statement as a circuit. And this, you can imagine that this kind of statement is related to having some address, like in some kind of Merkle tree. So it means that this results in, it's not very naturally encoded as a circuit, which means that you will have always like really large circuits here, which is what makes the problem difficult, because all these circuits here will have like, I don't know, 2 to the 20 gates. Okay, so
yeah. And these kind of statements are or now and then we need to add new statements and produce new circuits. And who does it?
Okay, so so I think that the way to think about this is sometimes there are, so usually maybe you don't need to change the circuit that much, okay? So because I don't know, like if you have to, you always proving, for instance, the same time, it depends on the application, of course, but like many natural applications, maybe everybody's proving the same circuit, right? Like everybody wants to prove the same type of statements. No, the circuit is the type of statement. However, in any update of the system, any modification that you want to make, so as we will see now, the point is that it can happen, so statements will change very often. The circuit will change once in a while, maybe because there's an update or in a typical context, okay? So who does this? Well, we will come to this, okay? So, but there's the way to see it, that there's some kind of agreement set by the context of what kind of circuit you need to prove. No? Like, for instance, what is a valid transaction? Well, there's a well-defined conditions of what is a valid transaction. Don't know if this is clear.
Thank you. It was very clear.
Okay. So this is the main step, and actually so you have to apologize. I don't know if this is what you wanted, but in this talk you will get quite some technical material, so I will be quite technical. The goal was, but I think that what I aim to transmit is what are the main techniques behind these constructions. Okay, so So what I wanted to show you is how to make a circuit. So how to first want to concentrate on this step. Okay, so let's say you have a circuit and you want to build an algebraic relation. Again, this was a very good question because I want to emphasize that what we will do here are very small examples, but we are talking. So the challenge now in SNARKs is to really have something that scales for really, really, really large circuits. So what we would like to have is a way to prove relations for circuits that are really large, and the larger, the better. Okay, so this is just a little example so that you understand. But all the time when I talk about the size of the circuit, which is the number of gates that the circuit has, or inputs will not be so big. So the inputs are something in the hundreds, sorry. So that we have a circuit that has some inputs and some gates, and the size of the input is not so big, but the number of gates and everything, which determines the size of the relation you want to prove, is really, really huge, okay? So here we have a very simple circuit. What does it do? Well, it takes 4 inputs. First, it sums these inputs, then and then it uses this input as the left wire of the last gate, and then it multiplies this input by 2 and multiplies it by 3, 3, 5, 6, 4. So you get something like that, okay? The first A, B, and C to refer like the left, the right, and the output gates of each gate. So let's say this is a circuit where this is wire A5, A6, this is wire B6, and this is the output wire C6. The left wire here is A5, and the right wire is A5. Okay. And the point is that you can see that I can break down the fact that this circuit is satisfied, so that this circuit computes the correct computation as 2 kinds of relations. So first, a Hadamard product relation. Hadamard product just means the point component wise product of 2 vectors. And what I want to show is that the left wire of the gate 5, so I call this is gate 5 because the output is C5, and this is gate 6. So what I want to see is that A5 times B5 is C5, and that A6 times B6 is C6. Okay, so that left times right is equal to output gate. So, and then I want to see some linear relation. So I need to see that A5, A6, sorry, which is the left wires, should be C1 plus C2, and B6, which is the right wire on gate 6, is just the output of the previous gate, and so on. Okay, so in summary, what I have is some quadratic relation I have that this will be simpler. I have just 3 vectors of the same length, which are A, B, C, which are assignments to the left, right, and output gates, and I want to prove that some quadratic relation is satisfied. I add a 1 to the left wires, to the output wires, because you also want to have gates that have are adding a constant or things like that, and then I can write just the Hadamard product relation of, the full circuit as a relation between 3 vectors of the same size, 1 quadratic and 2 linear relations. Okay, the details don't matter too much. The point is you have 3 vectors of the same size, and you have to prove that a quadratic relation holds, so that A, or Hadamard product with B, is equal to C, and that the A is has this linear relation with C. So each wire of A is a linear combination of some C values, okay? And same for R. Okay, so that's it, okay? That's the role of the circuit, to define two algebraic relations, one quadratic, one linear. So just to be more detailed, so imagine I have this circuit from ZP, the same one, that's from ZP4 to ZP, and my statement will be something like that. I want to say there exists some 3 and some C4. Three inputs are public, and the rest are not public, and I want to say, okay, and all this will evaluate to 84, okay? Something like that. Okay, so, and this breaks down my statement into 3 parts. A public part, some public input relations. I will not talk too much about this, but just to illustrate that we have these are the types of statements that I want to prove, and this quadratic and these linear relations, okay? And what is my witness? Well, my witness is all the partial evaluations of the witness C, okay? So in fact, the witness is, the witness is C1 equals, this should be a 2. The witness is C1 equals to 1, C2 equals to 2. No. Okay, this is the constant, and the C1 is equal to 1, this is C2 equals to 2, C3 equals to 3, and C4 equals to 4. Okay, so these 2 values are not known to the verifier, and if you do, if you compute the result of evaluating the circuit on this, you will get that the intermediate evaluations of C is just this vector, okay? So the vector that the witness that the verifier has is all the intermediate values of the circuit. And sometimes you can also think that the witness is also A and B, but it's redundant, okay? A and B can be computed from C. Okay, so what do we do with this? Okay, so we have now a set of algebraic relations, and we want to encode it as a set of polynomial relations. And for this, I have a multiplicative subgroup of a finite field. So this is a set of points in a finite field, which usually it's chosen as a multiplicative subgroup. So this means it's a set of roots of unity. For this talk, we will not really see why is this necessary, but the main reason is that because then we have algebraic optimization, so we can do fast Fourier transform and all of this. But for this talk, for seeing the correctness of the protocol, this is not necessary to know, okay? And we have, the important thing is that we have this polynomial, which is the lambda ith Lagrange interpolation polynomial, which you probably seen somewhere. The point is, what's the interesting thing about this polynomial is that it evaluates, if I have this, this set and it evaluates to 1 in Ri, and it evaluates to 0 if I is not equal to j, okay? Then the other important thing is that we have this vanishing polynomial, which is takes the 0 value at all the roots of all values at R. Okay, and finally I will be using this vector lambda, which is just the concatenation of all these Lagrange polynomials. Okay, it will be convenient to talk about not only polynomials, the Lagrange interpolation polynomials, but a vector of polynomials, because then I can do some kind of linear algebra. Okay. Okay, so sorry for all these technicalities, but what you have, the important thing to take in mind, to keep in mind, is that all the time what we're doing when we try to convert a statement that is written in algebraic form to a statement about polynomials, what we are doing is we are mapping vectors, no? So a vector of length m to polynomials, okay? And which polynomials? So this polynomial, which is just the inner product of the vector of Lagrangians times y, okay? How can you think about this polynomial? Well, you can think about this polynomial as just the result of interpolating this vector at this set of points, okay? Why? Because you can check easily that this polynomial is the unique polynomial that, evaluated at each of the points of R, evaluates to the vector y, okay? So this polynomial yes,
so,
please. Please do.
So I lost the connection between the polynomials and this evaluation. So if you are doing as an FFT transform, fast Fourier transform, there should be a representation in terms of the polynomial which you have the coefficients, and a polynomial which you have the representation by points, right? And
yes.
Which one corresponds to which one?
Okay, so for now, forget about the so for now, we don't talk about the Fourier transform, but the point is that we are mapping each polynomial. So we are using, this is the evaluation representation. So the point is, we are now here, we have a set of linear relations with vectors, okay? So you want to prove things about vectors for now.
Yeah.
And now I want to prove things about polynomials. So what I do is I interpret this polynomial as as the evaluation of some polynomial at this set of points.
Okay, so there are two different problems. This problem is about proving a relation on polynomials.
Exactly.
Okay.
Okay, so yes, because I want to, so for me in this talk, it's important all the time to understand the algebraic relations. So I don't want to move directly from circuit to polynomials, because this will be important, this algebraic interpretation. So we have two steps, okay? First, from the circuit, we go to some algebraic related that have to see, okay? So I could also, so I don't, these are not the coefficients of the polynomial in the monomial basis, is the polynomial evaluated at the set of points.
Yeah.
Yes?
Clear.
Okay. So, and the important thing now, so, okay, so what I tell you now is, what I just told you is, okay, for each vector, you build a polynomial, okay? So now, the important thing to note is that these Hadamard product relations that we had here, no? So we want to prove three things, but one of them is a Hadamard product relation. This is easily encoded as a divisibility relation, okay? So the point is that you want to show that A, so the component wise of product of A and B is equal to C. You can see this translates into this polynomial relation, where this is the vanishing polynomial, okay? So this is the polynomial that is zero at all these interpolation points, okay? And why is that? It's very simple, okay? The point is that this polynomial evaluated at R0, no, so at Ri, no, so this polynomial evaluated at Ri, some Ri, is equal to Ai. Okay, by definition, what is the evaluation at the polynomial A evaluation at point A is the ith coordinate of A. This is the evaluated B evaluated at Ri is the ith coordinate of B. And this evaluated at Ri is the ith coordinate of C. So what I get if I evaluate is that this is A, this is 0, because this is the vanishing polynomial, okay? So this equation, so what I get is that if I evaluate at each of these points of the domain, I get a different equation that tells me that AI times BI minus CI is equal to 0, okay? Which is the relation that I want to prove. Okay, this is actually a simple fact. So if it was too technical, just review this definition, okay? That each polynomial is mapped to the set. So each vector is mapped to a polynomial that evaluates to this vector at these points, okay? And you can easily check that this relation holds. In any case, the point is that now I already did part of the work, okay? What I wanted is to move all of this to as a polynomial relation. And I partly did this because I already have that the Hadamard product of 3 vectors will be, so 3 vectors will be in a Hadamard product relation, even only if there is some kind of divisibility relation between 3 polynomials. So now I want to do the other part, right? So what I now want to show is how to prove linear relations. And the difficult part, well, the main idea is that I can also encode each of the matrices that define the polynomial relation. So I can encode each of the rows as an equation at a different point of R, okay? So here, it's a similar idea. So here I have that when I want to show that the vector C is the Hadamard product of A and B, this amounts to proving M equations, okay? I encode M equations in linear algebra as a single polynomial equation of polynomials of degree M, okay? And each equation here corresponds to evaluating this equation at a different point in R. Okay, and here we can do something similar. So for each row of the matrix, I consider each row gives me an equation at a different point, okay? In other words, what I do is if I have a matrix, I can think of each of the columns of the matrix as I can encode it as a polynomial, so that I get that if I multiply this vector lambda times L, I get a vector of polynomials. If I multiply this polynomial lambda times R, I get another vector of polynomials. And these 2 linear relations, which is what I want to prove, amount to proving that the polynomial A of X, which by definition I said it's the evaluation of it's this polynomial, so it's the polynomial that evaluates to AI in point Ri, should also be of this form. So this polynomial should be a linear combination. Oh, sorry, this is a B. Okay, so this should be a linear combination of these polynomials that encode the columns of the matrix. Okay, so anyway, the point is that now I have these linear relations and I translate these linear relations into a problem about the columns of the matrix L or the columns of the matrix R with the same coefficient C, okay? So I get, so what you have to keep in mind is, going back to our example, is that now, even if you got lost in the way, so the important thing to know is that we, if you reconstruct all this argument, we come to this conclusion, okay? We started with a small circuit. We had to prove 3 things. We have to prove that some public inputs are satisfied. And then we also had to prove that some Hadamard relation was satisfied, and this is translated into a divisibility problem. And now we have to prove that, to prove the linear relations, what we need to prove is that there are 3 polynomials, A, B, and C, that are of this form. So they are a linear combination of some polynomials that have to do with the description of the circuit with the same C, okay? And I didn't tell you how to prove the linear relations yet, but I tell you, okay, all I need to do is to prove that A, B, and C are linear combinations of some polynomials that are tied to the description of the circuit with the same value C, okay? Now we move to the other, so as I said, we have two parts, okay? So first we have these information theoretic parts where we are doing nothing but rewriting the statement. And now we have this computational step where this, sorry, I have a problem with my mouse, with this, where this very large statement is compressed to a very, to doing a few checks, okay? And this is the fundamental step for having succeedness. If I want to verify the polynomial relation and I don't do these compressed steps, I still need to do a computation that is as big as the circuit, okay? But now I will do this compressing step, and I will do a very, with only one operation, I will be able to verify this equation. Okay, so very quickly, what is a bilinear map or pairing? I'm sure most of you know. So the point is we have three groups that are cyclic and they have order P. And we know that in these groups, the discrete logarithm is hard. So what this means is that if you give me, I have a point in the curve, Pi, and you give me A times Pi, I don't know how to discrete logarithm of A Pi in base Pi, okay? What pairings do is like they allow you to do some bilinear operation, okay? So given some element in the first group and an element in the second group, you can do this operation, and it's bilinear, so which means that each of the exponents alpha and beta here move to the exponent here, okay? And it's another degenerate map.
Sorry, Carla, maybe we can wait for a few questions from the audience if they have any, so to make sure just that, so for me it's clear, so I want to just make sure that audience are following.
Yes, for sure. I prefer if you interrupt me and ask me.
So any questions so far, audience? Please, if you have any question or
sorry, I don't know if it's like it's getting too technical. I'm not sure. Maybe I hope
it's fine.
It's fine. Okay.
Yeah, it's fine. We can follow it.
Okay.
Okay, so let's continue then.
Okay, so and I will be using, I insist I will be using this notation, okay? So AI is A times Pi, okay? So I just write the discrete logarithm of the in brackets, and this in subindex I indicates the group, okay? Indicates if I'm in G1, in G2, or in G3. So what can we efficiently do in these groups? So I don't want to talk so much about what we do in these groups, because at the end, the important thing is that this is the compressing step. So we don't need to understand much about these groups. We only need to understand why they allow us to compress this very large statement to a single point check, okay? So, and the key feature is that essentially all we can do efficiently in these groups, this is why they are called groups, because there's only one operation, which is, in this case, is the sum of elliptic curve points. And all we can do is essentially compute linear combinations with known linear coefficients, Ci, okay? So you give me some points, and I can choose some scalars and do this linear combination. That's perfect, I can do that. But I cannot do more complicated things. So in particular, if you give me some element, which is a polynomial evaluated at some point tau, so there is a secret point that you don't know. You only know it. You only know these powers of this secret element in the curve. Okay. What if you you can only compute this polynomial divided by so you can only compute p of tau divided by t of tau. Remember, t will be the vanishing polynomial at this set of interpolation point, but here it doesn't matter. But like, imagine you want to compute p divided by tau. So p evaluated at tau divided by t divided by tau. So if p is divisible by t of x, this is easy to compute, okay? Why? Because then you can compute this division formally, and then you just evaluate it by doing a linear combination, okay? So the point is, if this division, if this h of x, that is the division of p by t, exists, then this quotient is easy to compute. On the other hand, if p of x is not divisible by t of x, I don't know to compute this, okay? So in principle, this is well defined because this is t evaluated at some point, so this is just a number, right? It's a number in the finite field, so in principle, I can always divide by such a number, but the point is that this is not feasible to compute because I can only do linear combinations. So I don't know how to compute this quotient as the evaluation of a polynomial in tau. Okay, so with all these ingredients, this I already have, it's easy to do a SNARK. So, and this is the technical, this is an abstraction of the first SNARKs. So how would I do that? Well, you, for setup, you just choose a random point. The idea is this is a secret point that nobody, apart from the person that creates a setup, nobody knows, okay? And then you evaluate all these polynomials. So this is the vanishing polynomial at some set interpolation points. These are the polynomials that are associated to the matrix that define the circuit. And you just publish these polynomials in the curve, okay? And this is your structure reference string. So these are your trusted parameters. And how does the prover proceed? Well, the red part is for zero knowledge, so you just ignore it for a second. But the idea is that you create these polynomials, a of x, b of x, and you can do that because given all these powers of tau that you're given in the structure reference string, you can do linear combinations and evaluate these polynomials. So,
just to make sure that I understand the notation, so this 1 and 2, which you write in the beside the subscript of the bracket, is for the first group and the second group in the pairing, right?
Exactly.
Okay.
I think maybe that's not so important for now. So I could also maybe define it in bilinear, in symmetric bilinear groups, but just all you have to make sure is that you, when you do the pairing, you map things in that are in G1 with things that are in G2, and that's it. Okay.
Okay, but let me ask also another question, which is in a higher level. So the only solution that we currently know is on bilinear group, and we don't have any solution, let's say, based on the standard discrete logarithm or EDH assumption like that. Do we?
Yes, we do, but the point is that what pairing base gives you is like super efficient verification. That's really hard to get without pairing, because this bilinear operation, like the key is the bilinear operation, okay? It's very, this is extremely powerful to have a bilinear operations, and we have other constructions, but none of them has the efficiency for verification.
Okay.
And now I will show you how we verify this proof. Okay.
Okay.
So anyway,
can I also
yes.
add something there? And can we say that this is because of this public verifiability is because of this pairing? Because once we have this lattice-based stuff, they are not public verifiable. Basically, This is also another, I mean, advantage of this pairing base.
Yeah, exactly. So maybe my answer was maybe not complete. So what is difficult to achieve without a pairing is this public verification that is also constant size. No, the both ingredients.
Yes, thank you.
Okay, and well, anyway, and the point is that now we have all the ingredients, and from everything that I explained, the key idea for the proof is that what we do is to prove that the Hadamard relation holds. Okay, so what does it mean to prove that the Hadamard relation holds? It means that we can divide the product of A, B, and C by the vanishing polynomial. Okay, as I said before, this implies that A, B, and C have this Hadamard product relation. This is one part of the proof. This takes care of the quadratic part of the equation, and the second part of the proof shows me that is about showing that A, B, and C satisfy the linear relation, which means to show they have the correct form. Okay, so they are of this form. They are vectors that are linear combinations of these polynomials that are part of the description of the circuit, but with the same C. I want to say one more thing. First, and how do you verify this? Well, you first have to verify that these things are well formed, and then the key point is that you can check this divisibility relation by checking that this quotient times the vanishing polynomial evaluated minus C. Okay, so essentially with the pairing I can check this verification, this divisibility relation.
There is also a question here in the chat
yeah.
box. So somebody has asked that in the previous slide, I don't know which slide he mentioned or she mentioned, why do we have the relation to ensure non-degeneracy? In particular, I would like to know why we would need to hold while working with bilinear pairing.
Okay, as I said, the power of this is the bilinear operation, but non-degeneracy, well, this would not be really helpful, right? Like if, this would not be really helpful to have a pairing that always evaluates to 1, which is what this condition ensures. So I need to use this pairing to check bilinear relations. So you can see it here. Okay, why do I need this pairing for? Well, I need to check that these two things, these two products are the same. So essentially, I'm using the pairing to do products of points in the elliptic curve. So I can evaluate degree 2 polynomials in the elliptic curve, which is what I want, okay? Because to check the Hadamard relation, I need to multiply A times B evaluated at the point elliptic curve. So these are 2 points in the elliptic curve, and I need to verify a quadratic relation here.
Okay, thank you.
Okay, and so I just want to say something, and this is important for the rest of the argument. I didn't tell you how to prove this second part, so how to prove the linear relation. What we do is we include in the SRS a linear combinations with some coefficients alpha, beta, and gamma that are random, okay? So the idea is, so far the way I explain this, I have that my trapdoor, so the secret information in the SRS is some value tau. But in fact, I will also have other information in the SRS that is secret, so I will have alpha, beta, and gamma, and I will put this information in the SRS. Well, there's a bit of mismatch. Beta here, it should be in beta 1, in group 1, okay? It's a simplification. But, and the idea is that I will force the prover to compute this value, which is with the same coefficient Ci that he used for A, B, and C. He needs to compute this linear combination of the polynomials. Why? Because then we will check that the polynomial A times alpha plus the polynomial B times beta plus the polynomial C times gamma is equal to this thing. What's the intuition here? The intuition is that because the prover doesn't have alpha, beta, and gamma separate, okay? So he has it in the other group, but he doesn't have it in group 1. He is forced to use the same C in A, B, and C, okay? Because he only has linear combinations of alpha, beta, and gamma that go together in the SRS. To create such a proof, he also needs to use the same C for A, B, and C. Anyway, what is important for you to remember is that this way of proving all these values in the common reference string, okay? So this is the key thing to remember. Let me say a few things about security of this construction. So this construction can be, if you put the red parts here, you can see that has perfect zero knowledge. Why? Because this is just one point in the curve, and if you add this, you're completely blinding. You're completely randomizing A, so it leaks no information about the witness. Same thing here and same thing here. Okay, so and H is just defined to be uniform, conditional satisfying the verification equation. So actually, this is a zero knowledge proof. And why is this sound? So how would the soundness proof work? So essentially, there's the first part, which would, if you build the soundness proof, it would go like that. You first would extract a witness candidate from A, B, and C. I will say a little bit about this in a second. And then you can see that if the adversary breaks soundness, because of how we encode Hadamard relation, so we know that if this is not these polynomials are not correct, then this would not be divisible by the vanishing polynomial t. Okay, so when I said before we have Hadamard relation, we said A, B, and C are the Hadamard are in a Hadamard relation even only if p divides. Okay, they are divisible by the vanishing polynomial. If they are not divisible, the adversary has computed this quotient in the elliptic curve. But the important thing here is to note that the reason why this is impossible to do is because this trapdoor tau is not known. Okay. For Reynolds relations, the thing I want you to remember is this thing that I said before, is that it's important, so to make sure the adversary cannot cheat, sorry. It's important that alpha, beta, and gamma are secret, because you need them to be tied together to B, W, and lambda, okay? So in particular, what is very important to know is that these trapdoors need to be different for each set of polynomials. So for each different circuit, I need a different alpha and beta and gamma. And if you try to reuse them, you completely break security, okay? This is the two important points. Just one more sentence about the point, this idea of extracting a candidate. This is actually where we need very strong assumptions. I don't really want to go into this, but like these are a family of assumptions that are, my mouse goes crazy. So there is a family of this to extract, okay? I have something that is very short, and extracting means computing from this very short thing a very long witness. That's impossible to do information theoretically, because you cannot extract a very long piece of information from a short piece of information. And this is where we get very, very strong assumptions, that are assumptions that not only tell us that the assumptions that assume that adversaries compute things in a certain way, okay? So that we can look inside the code of the adversary and find what is the witness that they use for doing all this computation, okay? Don't want to go into this, just telling you that this is where the step where we need these very strong assumptions that I mentioned at the beginning, also called non-black assumptions, okay? But my focus is, since I'm running out of time, I wanted to focus on this universe, so on the setup, okay? So, and the lessons learned from all these universal and non-universal SNARKs is that the structured reference string has two parts, okay? And one part is just a part that is circuit independent or universal, okay? Which are just all the powers of the trapdoor, so all the powers of the secret information that need to be given in the SRS. If I have all these powers in the SRS, I can compute all these polynomials, okay? Because if I have a certain circuit without, and I have the powers of tau, I know the coefficients of these polynomials bi, wi, and lambda I, and I can compute everything if I have these powers of tau in the group. The other part of the SRS, okay, is circuit dependent. And as I said, these are these coefficients alpha, beta, and gamma that are used for proving linear relations, okay? And it's fundamental, as I said, in both situations, it's fundamental and gamma is not lit, okay? So it's super sensitive because as soon as tau, alpha, beta, or gamma is known, I can completely forge a proof of a SNARK. Related to your question, if this is used for proving that, if you use a SNARK to prove that a financial transaction is correct, you have lots of incentives to try to make fake proof, okay? So there is a lot of economic incentive to recover these trapdoors, because with this, you can just fake any transactions. So it's a very delicate process. And when we run the setup, as I said here, the setup means choosing this random tau, choosing some random alpha, choosing some random betas, choosing some random gamma. If this is not done correctly, and some information about these values is leaked, you can fake transactions, okay? Okay, so in summary, we have this part that's circuit independent, this part that is circuit dependent, that has to do with the linear relations, and they are both extremely sensitive. So this is why when Zero Cash, which was this for this cryptocurrency that was pioneering the use of SNARKs for privacy-preserving transactions, they ran a setup ceremony. So this means they were generating the parameters they needed for their SNARK, which is their SNARK was something similar to what I explained. They really made sure, so they did this in a multi particularly generate this structured reference string. But after the ceremony, they made this big display where they were destroying computers and everything to make sure that no information about the trapdoor could be leaked, okay? Because inevitably in the setup, okay, you need to choose the tau. I insist on this, okay? When you create the setup, you need to know the trapdoor. But after that, you want that this trapdoor disappears forever. Okay, so in a multi-party computation protocol, this problem is reduced because there is not one single party that has pieces that has the full key, but each person has a piece of the key. So you still want to make sure that this is deleted forever and cannot be recovered. Okay, so you can see here how they ran this setup to generate the parameters, and afterwards they destroyed the computers and so on. Okay. Okay, so you can do that. You can generate the parameters of a SNARK with a multi-party ceremony. But we still have two problems, okay? So one problem is that a multi-party ceremony to generate parameters is something that requires lots of effort, because it means many people have to be online, they have to be communicating with each other. You might still be suspicious afterwards, because you might be, okay, but who was in the ceremony? I'm not sure, I was not there, so how can I, who are these people? Are they collaborating or not? Anyway, so the point is that an MPC ceremony is still something expensive and once that this running the ceremony is something very costly and expensive, is even more acute because there is a part of the SRS that needs to be done for every circuit. Okay, so so this motivated there was this paper of Groth, Kohlweis, Mahler, Makel, John, and Myers in Crypto 18, where they propose a different model for generating the SRS. So the one thing you have to remember is that is this line here. Okay, so for the multi-party computation model, what we have is many parties that have to be online and communicated. In the updatable model, each party can just update the SRS and go offline. Okay, so the idea is each person contributes one little part of the SRS and then can disappear. Here we have that in this updatable model, we just require, like, what we want is that the final result, the final SRS, will be secure, which means nobody will know the trapdoor associated to this SRS already if one person is honest. Okay, so this would really greatly simplify SRS generation. If we manage to construct a SNARK that allows to generate the SRS in this model, this makes it much more simple to run a ceremony and generate parameters for a SNARK. For this, for Zcash, okay, these people, Bo, Gabizon, and Myers in 17, they have this paper called Powers of Tau, where they describe a sort of a ceremony for a SNARK like the one I described, for this sort of non-universal SNARK. And they already did something a bit similar. So they proposed to generate the SRS in two different phases, okay? One phase that was generating this circuit independent and universal part, which is this part, and another part, which was generating this circuit dependent part that was updatable, okay? So what they had is sort of an updatable model in two phases. What this paper proposes is to do a universal and single phase updatable setup, okay? So this is very important to understand. So please, Karim and Shahar, please ask me if you don't understand. So what we want here is to have a way to generate parameters that is universal, so that we do it only once for one circuit. So we only generate in a trusted way SRS that is good for every circuit, and that it's updatable, so that it can always be updatable. And then the circuit, we also do a circuit dependent part, but the circuit dependent part is more like a pre-processing. So there are no secrets in this pre-processing part, okay? Before alpha, gamma, and beta had to be secret. In this new model, we have is generating, is contributing a little piece of the trapdoor, which is the potential delicate point, this is only for a universal circuit. Okay, so how do we build these nice things, which are universal and updatable SNARKs? So again, we are in the same situation. So the circuit to algebraic relations part is the same. Okay, so we have a Hadamard product, and the thing to note here is that this is a universal relation. Okay, so I always want to prove, no matter what the circuit is, I always write it in such a way that I use one wire per multiplication gate, and I always have this set of quadratic relations no matter what the circuit is. Okay, but the problem that I had.
Sorry, Carla. So I'm confused with this concept of universal, which you say. So what are the inputs of this universal circuit that you construct? Is it another circuit and another?
No. The circuit is not. The circuit is not universal. Okay, this is a very good question. The circuit is not universal because, of course, there is such a thing as a universal circuit that allows you to prove that can encode any other circuit, but this introduces quite an overhead concretely. Okay, again, the situation is that these circuits are very, very large. Okay, so if you have to build a universal circuit that encodes all of these circuits that are very large, this gives you a very large overhead. With that, for is just powers of this value. Okay, so there is just one SRS that is powers of the trapdoor up to a certain value, and then you pre-process these polynomials, then you do some pre-processing of the circuit, and then you can compute other things in the SRS. Okay. Because maybe you say, now I want to, so I have this SRS that's universal that was computed by many people in a trusted way, so that nobody knows the trapdoor. And now I want to specify this SRS for my specific circuit, but anybody can do this, okay? Because there's no trapdoor.
Okay.
Clear. Okay.
Thank you.
So,
Carla,
yes.
Can we say that we sort of have removed the elements of the CRS that depends on the topology of the circuit, but we have kept the elements that they only related to the depths of the circuit. It doesn't matter basically how they are connected to each other, but it's only important that how many multiplication gate it has, for example.
Well, yes, but I want to, I think it's also important to stress that in the SRS, you will add things that depend on the circuit, because you need to pre-process the circuit, because this is a well-known thing, right? Like what happens if you don't pre-process the circuit, if you don't add anything in your SRS that depends on the topology of the circuit, this means somehow the verifier cannot be constant size. Okay. Because
okay. You mean later if you want to use this universal SRS,
exactly, but the important thing is that this process that you do later is not trusted.
Yes,
there are no trapdoors.
I mean, I got it. I mean, they are in basically linear relation.
So yes, you can say it as you explained. So there is a single universal SRS, and then now you say I want to prove this specific circuit. Then you do some pre-processing. You compute some things that have to do with this specific circuit. Okay,
I get it.
But everybody can do that. That's the important part.
Yeah, and I guess, okay, I get it.
So, and sometimes this is called the indexer, the person who, the party, there's supposed to be a party that pre-processes the circuit. But it can be anybody, okay? You can also think about it as it is as if the verifier was doing this work once. So the verifier pre-processes the circuit once, and from that point on, he can always verify in constant size. Okay, so anyway, the point is that the real problem that we have if we want to build universal SNARKs is that we don't know how to prove these linear relations in a universal way. Okay, for these linear relations, I really needed this alpha, beta, gamma that were really tied together, as you say, as with the topology or with the polynomials describing the circuit. So I really need to find another way to prove all these linear relations. Okay, so how can we do this? Well, as you say, as you know, like doing proving linear relation is very close to doing, it's related to doing inner products. And we have a way to encode inner products as polynomial relations. And this is called the univariate sum check, okay? So imagine you want to prove, again, we are in the same situation. We have these Lagrange interpolation polynomials, these vanishing polynomials, and we know that if we want to prove that Z is the product of W and Y, there is this lemma of Ben Sasson et al. In the Aurora paper that tells you that if this is the inner product, if the polynomial encoding W, so which, as again, this is the polynomial that goes through the vector W at the points of R, just as before. So this polynomial encodes Y. So the product of the polynomial encoding W with the product of the polynomial encoding X Rx plus HX times X. So again, it's a bit similar to as before. So we have this something that should be reduced modulo the vanishing polynomial. And the idea is that whatever, after I do reduction modulo the vanishing polynomial, I get something that is divisible by 0. So this was proven in Ben Sasson et al. And in fact, we have a very simple proof that we did in some paper that we have in, I have it referenced here, in Ràfols Apico, okay? And it actually has a very simple proof, okay? And the idea is that if you do this polynomial modulo T of X, you already know that this polynomial is the Hadamard product of these two vectors. So you already know that this polynomial is of this form because of everything I said before. And now if you evaluate to 0, and knowing that evaluation of if you are in a subgroup of roots of unity, so here I'm really using that this set R is a subset of roots of unity, the Lagrange polynomial, the ith Lagrange polynomial evaluated at 0 is m-1. Okay, so when you evaluate this at 0, what you get is that this is the inner product of Wi and Y1. Okay, so this will be 0 at 0, even only if we have this proof. Okay, it's not so important. I put the proof here. You can review it later, but the point is that this is not very complicated to prove. Okay, it's a relatively simple proof. And but essentially, we know how to prove one linear relation because we know doing an inner product, right? So if this was one vector with one single component, so the idea is this allows me, for this, I'm proving in one shot. So when I write a matrix times a vector, this corresponds to many equations. And by doing an inner product, I can do at most one relation, okay? So I would like to have something like this univariate sum check to prove not just one linear relations, but many. And this is where we have problems, okay? Because there is no efficient extension of the univariate sum checks that allows me to prove m inner product relations simultaneously, okay? So the relations I want to prove are a vector is equal to a matrix times a vector. So this means that each coordinate of A is the inner product of one row of L and in a vector, okay? So I would like to prove M of these relations, but I only know how to prove one in this polynomial version. Okay, so the solution is, okay, I only know how to prove one relations in this succinct way. So what I can do is, instead of trying to prove these many relations, I can try to collapse and prove all, instead of proving all these linear relations, just prove a single one. How, if I want to check that I have that a certain product, a certain multiply this matrix by a row vector so that I'm flattening the matrix to a single row, okay? And the idea is, if I'm doing a combination of the rows that is sufficiently random, proving all these relations is equivalent to just proving a single one, okay? The problem is, this doesn't really solve our problem, because although the matrix is public, so the verifier could compute himself this collapse circuit, so this collapse matrix, this in general takes linear time, right? The verifier cannot afford to check that given the matrix W, this is a vector in the row span of W, because that's too much work for the verifier, because we want the verifier to be constant. And you have to think that this matrix that encodes the relation has as many rows as A. So it has as many rows as the number of gates of the circuit. So this matrix in general will have something like 2 to the 30 or 2 to the 20 rows. So we cannot ask the verifier to compute a linear combination of all these rows, okay? So what we need to do is somehow let the prover collapse this row and do this linear combination so that it only proves one linear relation in such a way that it can be verified by the prover that it was done correctly. Is this idea a little, is this okay? Okay, so now we try to prove this concept. So this idea of collapsing, no? So I'm trying to sample. I have a matrix, and I want to compute a vector that is in the row span of this matrix. Why? Because I want to collapse all these equations that one have to be satisfied into a single one. Again, now I'm trying to express this algebraic relation, which says I'm sampling in the row span of this matrix into a polynomial relations. Okay. In algebraic terms, what I want to do is to sample a sufficiently random vector in the row span. So it means I want to multiply a vector times m. Since what I do, so the vector that collapses all the relations of all the rows of M into a single row should be pseudo-random, okay? Because the idea is you want the prover to just prove this single relation. So, but of course, the prover should not know in advance how all these relations will be compressed, okay? It's very important that this is a random linear combination, because otherwise the prover can cheat when he reduces many rows to one. Okay, and the point is that if we define this this vector D in the row span of, we can think of this vector as a partial evaluation of a polynomial. Indeed, okay? So we define this polynomial, which is a bivariate polynomial that encodes this matrix M in this form, okay? So I'm multiplying on the left by the Lagrange evaluated at some variable, and on the right by the Lagrange polynomials evaluated by another variable. This gives me a bivariate polynomial. And if I want to sample this vector, this corresponds to, this should be interchanged. This should be, I'm evaluating y at x, okay? So I'm multiplying lambda 0, lambda m minus 1 times m times this. And this gives me the partial evaluation of, this is a partial evaluation of this polynomial x. Okay, so what does this mean? It means that if I want to sample a vector in the row span of M, this is equivalent to saying that I want to do a partial evaluation of a certain polynomial. Okay, so with these ingredients, I already have a way to do a universal and updatable SNARKs. Okay, how do I do it? Well, I compute these bivariate encodings of the matrices that I need. Remember that the relations that I need to prove are these. Okay, I need to prove that A is equal to LC and B is equal to RC, so which means it's the same as proving this single relation. And what I do is that I do bivariate encodings of any of these blocks. For just sends a challenge X, and the prover just samples that's the partial evaluation of these bivariate polynomials associated to the matrices I and L. Afterwards, he also needed to do it. Sorry, this is for the right matrix R, and so that these polynomials that are the partial evaluations, what they are is the encodings of some vectors and that are in the row span of minus I and L, okay? So, and at the end of the day, once he has done this, the prover needs to show that this linear relation holds, okay? So you want to prove that that A is L times C, and what you prove is that the collapse identity matrix times A is equal to the collapse L matrix times C, okay? And you can do this with polynomials encodings, okay? Why? Because we know if we have this, the encoding of this vector, which is the I, the encoding of this other vector, which is this partial evaluation, we have A, which is this polynomial, we have C, which is this polynomial, and we also have a way to do inner products when we encode vectors as polynomials. So we know how to do everything, okay? We have the Hadamard product relation, we encode ABC as polynomials, we prove the Hadamard relations as polynomials, we sample a there's only one problem here, which is here. How can I verify? So the difficulty here is that the verifier doesn't know that these partial evaluation were done correctly. Okay? So, and this is actually the main difficulty that was identified for building universal and updatable SNARKs. So the real difficult part, because Hadamard product, inner product, everything we know how to do, but we have to find a way to prove that these partial evaluations, which correspond to sampling vectors in the row of some matrix, are really done correctly. So this was what motivated us, so me and my co-author, Arantxa Zapico, to really study this block, so study how to prove this part, the partial evaluation was done correctly, separated. Okay, so we identify a sub-argument so the way we came to this is we were studying how people were building universal SNARKs, and we noticed that the difficult part was this, no? Proving that how to collapse many linear relations into one. So we isolated, we decided to study this separately, okay? So we defined something called a checkable subspace sampling, which will be a protocol that will allow me to show that a certain polynomial is the correct partial evaluation. So in some sense, what I'm doing is encoding the fact that I'm sampling a vector in the row span of a matrix with some coins given by the verifier, okay? So the partial evaluated are defined by the coins of the verifier, because we want this partial evaluation to be random, because we want to check one random linear relation, okay? So we can isolate this subargument and just focus on studying this, because this is the real difficult part of a SNARK, okay? So we define this, a checkable subspace sampling, and it's a protocol that has some pre-processing phase, okay? So you have a matrix, you want to prove linear relations for this matrix, and you pre-process a vector in the row span of W with these coins, and a proof sampling phase where the prover will convince the verifier that this D of X is sampled correctly, okay? Which was the difficult part here. I didn't tell you how to do, okay? So for now, we don't have a SNARK because we don't know how to do this part. Okay, I know I'm running out of time, but I will just finish very quickly. You can see I'm about to finish. But the point is, so the question here is, how can we, when can we build efficient checkable subspace sampling? So in our paper with Arantxa Zapico, we were studying this, and it turns out it's not easy to build these checkable subspace samplings for any kind of matrix. So in fact, Marlin, so you can do it for very general matrices. For instance, Marlin and our work partly was came about as an abstraction of Marlin, can do it for any sparse matrix. So which means that in practice, this means that you can do checkable subspace sampling, which allows you to do universal and updatable SNARKs for any matrix of these forms where L and R are sparse, which is general enough because this is the case in every practical application. But we were interested in seeing all kinds of matrices and how efficient can we do, and so on, okay? And so we found out, for instance, that we can do very efficient CSS for matrices with a bounded number of non-zero elements per column, which in terms of the circuit, this means that for circuits of bounded fan-out, okay? So for and then we have also some theoretical results that tells you that for matrices with low tensor rank, you can also do that, or any combination of those. Here is an example of a checkable subspace sampling for sparse matrices. I will not really describe the details, but just this is the simplest checkable subspace sampling that we have, which is for sparse matrices. So To keep in phase, so there is a pre-processing space. We just compute these two simple polynomials. And then in the proving phase, we just have to prove that there is the prover just have to find this polynomial h of x, and so that this equation verifies. Okay, so you can see that this is relatively simple. Anyway, the last remarks I want to make is why is I think there are different ways of so these are my concluding remarks. So there are different ways of trying to express a universal and updatable SNARKs as a sum of different building blocks. But I'm really a fan of this construction of checkable subspace sampling, because it really is not only that I think it's algebraically expressive, so it really tells you what's going on. So you're trying to compress many relations into one, but also because actually building a checkable subspace sampling is a significant part of the cost of universal and updatable SNARKs, okay? So if you look at different constructions of universal and updatable SNARKs, in fact, the main difference between them, in some sense, is this, how they deal with this problem of how to reduce many relations to one. And it's also, like, for instance, in Marlin and things like that, it's also a significant part of the cost of the total of both communication and proven to delegate this checkable subspace sampling argument to another party, okay? Because this is the interesting part about this checkable subspace sampling is that this is a computation that is done because we want the verifier to be constant size and efficient. But actually, everybody can do this computation, okay? Because the matrix is public. So this is a partial evaluation of a polynomial that is public, because it encodes, it has to do with the specification of the circuit, and the X is also public, okay? So because the X comes from a challenge from the verifier. So the point is that in these SNARKs, there is this part that is relatively costly, but it's a part that anybody can do, okay? So in future work, we actually investigate how to delegate this work to a server so that each prover can be much more efficient, and so by delegating this public computation, okay? So in general, you can also think of a model where you delegate the computation of a SNARK to a powerful server, but this has problems because you maybe not necessarily want to share your circuit. So your witness, sorry, because this is for privacy, okay? But this is public computation, so it's a natural candidate for delegation, and this is what we study in future work. Okay, I'm done, so I would like to hear questions.
So thank you, Carla, for a nice presentation. So even though your talk was quite technical, it was very enjoying and easily followable. So at least for me, it was very informative. There was a lot of part which I had only heard of, but I had never had the chance to hear the details, and it was a very good opportunity. Thank you. Thank you. So we are waiting for a question from the audience. If there is any question, we would be happy to hear. So meanwhile, I have a maybe very naive idea. I want to know what's your opinion. So the problem is that somebody wants to prove convince a verifier that a statement holds true, right? And we want to do this efficiently and succinctly, right? So if we somehow recurse on this procedure, and the proof that this is valid is also, we want to prove it in a shorter way. Do you see what I mean? So you want that proof that somebody wants to convince somebody that something holds true. Let's say that he convinces a third party that this proof is correct. He has already checked it and it's correct. Wouldn't it be somehow easier to recursively do this and come up with much simpler and shorter proofs? Has already somebody.
So you mean okay, so what you mean, that somebody, some designated party gets convinced, and then he tries to convince
Then you end up delegation the proof. So you delegate the proof for a third party, and he checks the original proof. But now you just need to verify the proof that was done by the delegator.
So, but I think the problem is that well, I'm not sure I understood like completely, but like if you mean that I can convince somebody, so do a proof for a designated verifier who can later convince somebody else. That's what you mean?
No. What I mean is that somebody who wants to verify the proof, he needs to do some computation, right? Now,
Yes.
what the idea is that he wants to do it more efficiently. He asks for the help for a designator. He checks the proof, which might be more expensive, but the verifier himself tries to check a simpler proof.
Okay, so a proof of a proof, no?
Yeah,
But
something like this. You can think of
okay.
it as a recursion on the proofs.
Yes, partly this is done, but like partly there are all kinds of problems related to this too. Okay, because for instance, like if you want to create a proof that a circuit that the verifier accepts a proof, you have to encode, like as usual, like anytime. I hope that at least this I made this clear. So anytime you want to make a proof, you need to encode it as a circuit that has inside the circuit of the verifier.
Yeah.
Okay, so and this can create problems, like for instance, if the place where you're defining your original proof is not the same field of definition where the verifier defines the proof. So this was for instance, this, imagine you have a pairing, no, like in this case, a pairing based proofs, and the circuit of the verifier has to do pairings and all this. Okay, so your original circuit was in ZP, where P is the order of the curve. The circuit of the verifier is a circuit that has points of so is able to do pairings and so on. So it has another field of definition, which is the field of definition of the points of the elliptic curve. So this starts to get a very complicated circuit because you have to do non-native arithmetic. So you have to do arithmetic of one field for another field and things like that. So you can, in principle, it's possible, like, but you have to deal with many problems of this sort. Okay, so how to write the verification circuit, the circuit of the verifier in an efficient way in some kind of circuit.
Okay, thank you.
Maybe to mention one application related to this that it is already used as that, Shahram. This idea was proposed first time by Ben Sasson et al. And later was used in Mina protocol. That is a ledger verification. You cannot verify the huge blockchain yourself. So someone does that and then gives you a proof that I verified the ledger and it's okay. And this is based on that one thing. I mean, this. Yeah,
Is
it's
there
in
a
the
question
chat box.
in the chat box?
Maybe I can read it. For CCS, does it replace pairing for succinctness? Carla, this question is for you.
So you need a pairing to verify the CSS.
Yeah. Okay.
I don't know, it doesn't. So, so I didn't mention this, but all these, it's not necessarily, like you could also do it in another way, but like all these universal and updatable SNARKs, the way they do is like you commit to these polynomials all the time. And then to verify the equations, what you do is like you open these polynomials at some point in the field. So it's a bit different from the original SNARKs. And then to prove that opening is correct, you use this Kate this KGZ commitments. But to make this link so that you have the polynomials committed and then verify the divisibility relations or whatever you want on the field, you need to make sure that these polynomials correctly open to a point, and this you do it with a pairing. Because the KGZ commitment needs a pairing to verify the evaluation.
I see. I hope this answers the question of this Ayman. So I had another question, Carla, maybe a little bit extended. So thank you for your great presentation. I learned a lot, personally, even I'm working and linear. But the point is that you mentioned that the verifier sends challenges, so that this protocol is interactive, but we can make it non-interactive using random oracle. And we know that the only CRS-based SNARK was the first construction by Groth et al. And in recent work, we tried to see if we can have something, again, just in CRS model without random oracle. But we couldn't, because we just had the succinct CRS, just constant public element, but it's still linear proofs. So I remember that once I asked this question before this result I had, and you said it's quite maybe difficult. I don't see any point. But what do you think at this stage that we have succinct CRS and the linear?
Okay, that's a great question, and in fact, thank you for asking, because I would like to make this point. So I hope what I wanted to make clear in the presentation is that the reason why the SNARK cannot be made non-interactive easily and efficiently is precisely because of the problem with these sum checks, that you cannot prove many relations non-interactive. So there is not a simple lemma that allows you to prove M relation at the same time. So you really are bound to do this probabilistic compression and prove all these, so reduce all this relation to a single one. So in some sense, the only part that really needs the random oracle is the CSS. If you take the CSS out, you don't really need random oracles. Okay. Why is this? So, and this also relates to quadratic SRS. Okay, in the sense that there is an which is adding more random variables in the SRS, so that you can essentially use a different variable for each row of the matrix. Okay, so let's say, well, this is complicated to explain if you haven't worked so much in SNARKs, but the idea is that you can compress all these relations also by adding more trapdoors in the SRS. Okay, but you need to add one trapdoor or one power of the trapdoor for each row of the matrix. So for as many relations you want to prove, and this matrix has the number of rows depends on the size of the witness. Okay, so this is why you need, so either you go for random oracle or you go for a quadratic SRS, and that's the situation. And quadratic SRS, for the audience, if somebody is like, it's a no-go, okay, because this is huge. insist, no? Like this is a 2 to the 20, 2 to the 30, so like you cannot have something that's quadratic in the series because it's too costly.
I see. Thank you very much.
Okay, thank you, Carla.
Thank you.
If there is no other question from the audience, so we say goodbye to you, and we will be waiting for the next talk in 40 minutes. Okay.
Yeah, Carla, just
Thank
can
you.
I ask to also share the slides because people are already asking about the slides. Thank you. I can use this time.
Yeah, let me fix one,
Yes.
2 typos, and then
Okay.
I will
Thank you very much.
send them
Okay.
to you.
Thank
Okay.
you.
Goodbye.
Goodbye.
Thank you very
Goodbye.
much.